Hi, I'm Angeline Lau. I'm from Mathematics and Statistics Department of De La Salle University. I'm a woman in STEM. In this STEM empowerment talk, I would like to share with you the exciting journey to the field of mathematical biology. Since I was a kid, not to mention how long ago, I already know that I only wanted to spend my life working in academia. I enjoyed solving mathematical problems and proving mathematical theorems. Way back then, I was also fascinated by the computing power of mathematical algorithms and how elegant it can actually be. So when I thought I needed to choose only one between mathematics and computer science, I found the Bachelor of Science degree program offered by De La Salle University in mathematics majored in computer application. It was like hitting two birds in one stone. I was thrilled and happy to get a step closer to my dream. I went to graduate school afterwards to strengthen my foundation in mathematics. I realized that mathematics is really important, even in the fields of computer science. So, on my second year of graduate school, I got the chance to know about systems biology. Systems biology is a holistic approach to decipher the complexity of biological systems. It is an interdisciplinary field wherein mathematics plays a crucial role. I belong to the first batch of students who enrolled in systems biology when it was first offered in the Philippines and for the first time at DLSU by Dr. Eduardo Mendoza, a Filipino researcher who is based in Germany. I was really amazed to learn how mathematics can be applied to study complex biological systems and how can studying the systems help in designing drugs and in delaying or treating diseases. And my journey to mathematical biology officially started. I will share in the next few slides some simple illustrations of how simple mathematics is applied to study biology, how mathematics applied existing tools and develop new concepts to embrace problems and questions posed by the biologists. Particularly, I will focus on the applications of dynamical systems model in biology. So I will start with the classical predator-prey ecological model. Predation is a relationship in which a member of one species, which we will call the predator, consume members of another species that we will call the prey. In this illustration, we'll consider the situation between rabbits and foxes. Foxes feed on rabbits and are dependent on rabbits for their survival. Though if foxes didn't feed on rabbits will get overpopulated and foxes will starve and might eventually go to extinction. So while the existence of the fox is a threat to the rabbits, but the existence of the fox itself is necessary for the stability of the ecological system. And this prey-predator model, structure model, was first proposed by Alfred Lotka and Vito Volterra. They actually proposed it independently in 1920s. That's why the model is now well known as the Lotka-Volterra equation model. Okay. And this described the predator-prey system. This is one of the classical and famous dynamical systems model. It has been generalized and applied to other fields of study. To elaborate, the Lotka-Volterra model or equation describe an ecological predator Y and prey X model, where A denotes the growth rate of the prey, B represent the parameter rate at which the predator destroys the prey, and then C is the death rate of the predators, D is the rate at which the predators increase by consuming the prey. And in this model, a prey population X increases at the rate of A times X, okay? And is simultaneously destroyed by predators at the rate of negative B times XY, okay? So in short, this equation means that the change of the prey's number is given by its own growth, which is AX, minus the rate at which it is preyed upon, which is BXY. And then the second equation is a predator population equation or representation. So the predation population decreases at the rate of negative CY, but increases at the rate of DXY. Okay? And in short, this expression or equation expresses the change in the predation population, okay, as growth fueled by the food supply when it eats the prey, DXY, okay, minus the natural death rate of the predator. In turn, this implies that the generation of both predator and prey population are continuously overlapping, okay, which you will see in the next illustration. So the population density of the predators decreases when there are few prey, as you can see from the first part of the slide. So when you have few prey, the population of the predator also started to decrease because they don't have enough food. So the population density of the predator started to pick up when the population density of the prey also picks up, as you can see in this part or section of the simulation. At the minimum number of predators, okay, which is here, the prey population reaches, okay, at some point its optimal or maximum population density. But this eventually increases the predator's population density to its max, which is here. And it can be observed that the population density of the two species are dependent to one another, okay, dependent on the population density of one another. And this beautifully reflected the relationship of predator and prey in the ecosystem and nicely illustrated how mathematics can be used to mimic or abstract ecological systems. One may also plot parametrically using a phase portrait or phase space without representing the time. So here we have the relationship of the number of prey and the number of predators in the y-axis. To better interpret this, okay, the orbit that we see actually follows the oscillating density population plots of the rabbits and foxes, as you can see here. Okay, observe that the intervals of x-axis for the rabbits, this is for the rabbits, and the y-axis for foxes corresponds to the amplitude that you can actually see here. Okay, the amplitude of the oscillations. For the rabbits, it's around 1.5 to 6. And then for the foxes, it's around 1 to 4. Okay, so at a given fixed point, this is your fixed point. Okay, the population density of the rabbit goes up from 1.5 to 6, which is this interval, 1.5 to 6. Okay, so it goes up from 1.5 to 6, but it also goes back from 6 to 1.5, from 6 to 1.5. Okay, whereas for the foxes, you look at the y-axis, it goes down from 2 to 1, okay, here 2 to 1 goes down, then up from 1 to 4, okay, 1 to 4 in the y-axis, 1 to 4. And then down again from 4 back to 2, okay. So the prey-predator dynamical systems can be applied to other biological systems that if it behaves similarly, okay. For example, it can be applied to an SIR model. Okay, what is an SIR model? S pertains to the susceptible population, I pertains to the infected population, and R for the recovered population. Okay, so for the change in the susceptible population, so let's focus on the first equation. Okay, the change of the susceptible population is given by its own population growth minus what? Minus the rate at which is infected by the population upon interaction with the infected population. Okay, and then it's also affected or decreased by the natural death rate, mu s. Okay, this is similarly represented for the changes in the infected and the recovered population. So with the SIR model, it can then be applied in general to any epidemic spreading of diseases like problem. For example, tuberculosis. Okay, So in this illustration, this is in this model, they have a homogeneous and 6-compartment model where S pertains to the susceptible group that are unimmunized. Okay, so you have the SA for the unimmunized, and then SB for the partially immunized group. Okay, and we also have the LA for slow latently infected, LB for fast latently infected, I for actively infected and undetected group, and then T for actively infected, detected, and or treated population. Okay. Similarly, we can also apply this to avian influenza. Okay. We can create our own scenario to determine and assess the control strategies proposed, okay, to stop the spreading of the diseases. So in this case, they actually propose 2 control strategies. One is through isolation and treatment, and the other one is through vaccination. So through these 2 different models, they want to assess which control strategy is more efficient in decreasing the number of infected population. So from the differential equations of the influenza virus, so this is the corresponding representation or ODE model of the influenza virus. You can find the similarities to the previous SIR model, okay, with an effect. So here we define the infected target T cells, T, and then I is the infected cells, and V is the infectious viral titer. Okay. Can also be applied to model tumor cells. Okay. Similar to how we model the prey-predator relationship, the SIR models. Okay. This is how we can represent the tumor representation in different regions to predict the antigen presentation in different regions. This is also widely applied in studying gene regulatory networks. So we have here genes 1, genes 2, gene 3. These are the expression level of each genes as a variable. So they are dependent variable here. And observe how similar are the cartoon illustration of the species predator. So on the left, we have the species predator representation, where you also use an arrow and an inhibition arrow. Okay, so observe how similar their graphical representation. Okay, and in the illustration on the right, we have here genes 1 that activates gene 3. Okay, and then so while it activates gene 3, that actually increases the expression level of gene 3. So once you increases the level of gene 1, which is the red line, okay, as it increases, it slowly activated the expression level of gene 3. Okay, similarly, it also activated the expression level of gene 2. As for gene 3, it inhibits gene 1, okay, and it limits the growth of gene 1's level expression. Hence, when you see that the expression level of gene 3 started to increase and pick up, okay, the expression level of gene 1 started to decrease, okay, because the expression level of gene 3 somehow, okay, will limit the growth or expression level of gene 1. Okay, and this is represented by the differential equations here. In this classical work, Ferrell et al. Explored what it takes to get oscillation out of the 2 simple types of circuits. So here we have 2 types of circuits, negative feedback loops and coupled positive and negative feedback loops. So they also try to determine in this model whether a given ODE model, represented here on the left, and a particular set of kinetic parameters, which parameter will produce this oscillation. Okay? Which parameters will cause this oscillation, which is a natural phenomenon or behavior of a cell cycle. So mathematics can be applied to other various fields of biology, to biomedical applications, to cellular physiology, food processing, social sciences, and even Earth's dynamical system. We now see many opportunities to apply classical modeling methods like dynamics of diseases to emergent world problems, as evident in the recent COVID-19 pandemics. So young researchers like you can actually contribute to such fundamental challenges while you build up your research portfolio along various other directions. In my mathematical biology journey, I learned to love both mathematics and biology more. I learned to appreciate them more, and I love what I'm currently doing. Um, I'm doing it because I enjoy doing it, I'm passionate about it, and the process itself of finding mathematical solutions is always an enjoyable and exciting experience for me. I hope that you pick up something from my talk and get some inspiration to find and do what you are passionate about. I'd like to acknowledge the following. The Center for Complexity and Emerging Technologies, Sensors, Systems, and Computational Biology Research Unit, Ernesto Rufino's brother C. John Lynam, FSC, and brother Albinus Peter, FSC, professorial chairs in mathematics.